second. Yeah. So bounded above. Okay. So all we need to check is this. So we need to develop techniques for this. That's all. Okay. So a few techniques that we already know and a few techniques which I had given in the problem sets, which we will discuss the ones you couldn't do, but otherwise it's not that difficult maybe. So
Can we also show
mhm.
boundness by this squeeze theorem?
Yeah. So the squeeze theorem is really what, no, but squeeze theorem is more specific. Okay, so the sandwich theorem or
Okay.
whatever squeeze theorem is more specific. So what? So what the sandwich theorem? Even the goal of sandwich theorem is slightly specific. So the goal of sandwich
Mm.
theorem is, as you probably know, but I am just saying it again, is that what the sandwich theorem says is that suppose there is a sequence S1, S2, S3, and so on. Okay, so I think Noel has entered. So Noel, are you here?
Yes, sir.
Yeah. So it's fine. We have just started. We were waiting, so we just started right now. Okay.
Sorry, sir. I was in the park. Yeah.
Oh no, it's
Sorry.
fine. It's fine. Yeah, it can
Yeah.
happen. Yeah. So this is
So,
okay. So we have not yet done anything. Okay. So we are just have set up the context that A1, A2 is a sequence. Okay. We want to add these. Probably we want to give a meaning to this. I mean, just to right, and we give a meaning to this by using the partial sums, right? S1, S2, S3, and so on. And the limit of
yeah.
these SIs we define to be this quantity is infinite sum. Otherwise, infinite sum decision, what is an infinite sum, can become a problem to decide, right? So that's all. Okay. And we are only dealing with the
Yeah,
case,
yeah.
Noel, we are only dealing with the case in which all the terms are positive. Okay. The case for negative is more difficult, so we're only doing the positive
Okay.
one. And when you do the positive ones, then the partial sums are increasing, right? Obviously,
Hmm.
right? And the partial sums are increasing, so we just need to show that they are bounded. That's all. Okay. So yeah, so now we're just trying to show the squeeze theorem also does the bound kind of thing. But see, the squeeze theorem is something like this. If you have a sequence S1, S2, S3, and so on, and
Yes, sir.
if you
Yes.
can if you can put SI between two sequences, okay, I should not use AI maybe. If you can put SI between two sequences, MI and M and NI, okay,
Yeah.
and if the limit of Ni and Mi is same, okay,
Yeah. So then the limit of SI is same because of sandwich theory.
yes, okay.
Yeah.
So now do you see, Mahima, that why this is a little different from what we are trying to do, right?
Hmm.
This is a more specific. This is also putting bounds, but this is like putting bounds on two sides and trapping the sequence in between.
Yes.
And this is strong in.
Also,
Mhm.
yes, yes.
No, I was just saying that
Continue.
when we have this, that the limits of both the upper bounds and lower bounds are same, then it also implies that the limit of SI will exist. So we don't even need to prove that.
Exist.
Yeah.
Hmm.
What were you saying?
No, how can we prove the squeeze theorem?
Okay. So the proof is not difficult. So to start with, what you can simply do is you can first do a translation, right? Which means that you can assume that the limit of these two things are zero. It's like a translation. So what I'm saying is that
Hmm.
you subtract by L. Okay.
Yes.
So that
Okay.
we can assume, that's always a good thing to do. It's like a normalization again. So the limits of Mi and Si is zero. Okay. So now what do you want to show? So let's write that first. Though intuitively I can say in the air, but it's better that I say it properly. So see, we want to show that limit Si. Yeah, usually squeeze theorem is never proved because we say it's intuitive, but intuitively it is clear, right? Hmm? But we will do a proof. So we want to show that this is zero. Okay. So basically you start with an epsilon. So you start with an epsilon greater than zero, epsilon greater than zero given, right? So if epsilon greater than zero is given and you want to show that there exists a n or there exists a n naught such that for all n bigger than n naught, what do you want? You want Si to be between epsilon and minus epsilon, right?
Yes, sir.
Is it okay, right? This is what we want clearly. Yeah, I'm just, yeah, it's clear, but I'm still just asking. Yeah. So this is what we want. Now, whose help do we take for the upper bound? Of course, we take the help of Mi,
Am I?
right? Because we know that we can find n1, right? Such that for all n bigger than n1, Mi is less than epsilon. Because Mi is
Hmm.
limited also. Some n1, that n1 we don't know. Okay, and for the lower bound, whose help do we take? Ni. So just
And I.
yeah, not naturally. So we just take n2, some other n2. We don't know the same n will work or not. Some other n2 we take. Sorry, such that this is bigger than negative epsilon. And so if you take the help of both these things, then what do you get? Mi, and this mi guy is less than epsilon, and the ni is supporting from below, and that's bigger than minus epsilon. And so si is between epsilon and minus epsilon.
Hmm.
And you so now your n naught will be the maximum of n2 and n1. Right?
Okay. Hmm.
Right, yeah, your n naught has to be bigger than both n1 and n2. That is important.
Hmm.
Okay,
Yes.
you understand. Yeah, this is very important. And when you are doing the same theorem in n-dimensional case, then sometimes what might happen, let's say in two-dimensional case, if you're doing, let's say that each SI is a tuple of number, right? And this tuple is bounded above and below, like some MI and NI is for this, and for this tuple, some TI and RI is there. Then you will have four NIs. And if you
Hmm.
take the maximum of those four for everything to work. You understand? So this can
Yeah.
extend
Yeah.
in finite dimensional cases, but in infinite dimensional this may not work
Hmm.
because you may not have the max. So that gets a little, yeah. But yeah, that is not needed at all. That's by no means needed for us. But it is the proof is this is like this, very simple. So yeah, the squeeze theorem is very important. We have not done it much, but that will probably just you solve problems and you can see you will encounter a lot of problems. It's not a very specific trick. It's a well-known thing. Okay, so basically, we want to develop techniques to put upper bounds because that's all we need, right? A bounded monotonic sequence is convergent, right? Noel, you also know this, of course, right? So
Yeah.
yeah, so since this is increasing, we just want to show that the SIs are bounded. So what is SI? SI is partial sum A1, A2 to AI. So you want to show techniques, okay? So naturally, if you want to show techniques of boundedness, if you can compare, so this comparison thing is the key, right? This is the root principle behind the ratio test and the root test, and rather many tests. Okay, there are hundreds of tests, and we'll say something about all the tests at once also at some time. The comparison is the key. So what I'm trying to say is that if you can find, if so AI is a sequence of interest for us, okay, but if this is very obvious statement, but I'm just writing out, okay, if you can find a bi, a sequence bi, such that of course bi is all positive blah blah blah, and bi is, and summation bi exists means that it's convergent, right? If you can find this, and if you can bound each ai by bi above, right? If this also happens, then job done, right? Isn't it?
Yes. Okay.
So if this is so trivial, but this is the core principle. If the BIs, if the BIs are summation BI is bounded, then this, and this is really, if you remember, Mahima, that this is what really we used to show that this sequence was divergent. We used the opposite of this, right? We bounded this
Hmm.
below by a sequence which was divergent, so this would obviously be divergent.
Divergent. Hmm.
So this is the
Okay.
core principle, okay? But see, this sequence here, it diverges, but it diverges very slowly, in the sense that we had to take a lot of terms, right? We had to take um so we had to take like 1 by 3, 1 by 4, this was bigger than 1 by 4 into 2. Then we had to
Hmm.
take four terms here, right? Noel, I think you have also seen this argument, right? 1 by 8, and
Yes, sir.
each of them is bigger than 1, each of them is bigger than 1 by 8. You have to take four times. See, so you are able to bound it below by a sequence which is divergent, and hence this is divergent. This is just the opposite principle of that. Very simple, but in most of our level of problems this will be useful. But we'll see how the ratio test is a very deep generalization of that. So but it diverges slowly, as you can see, right? Because you need to take four terms and eight terms and 16, so it diverges slowly. So anyways, that's quite okay, that's not a problem. So this principle, now usually what we do, actually we usually compare it with some well-known series. Usually this will be a geometric progression, usually,
Hmm.
okay? We if it's not, then it means the problem is hard, okay? Usually it's a geometry progression. But sometimes what happens is, and I can give you an example in this place, will be better, I believe. And this is, now we are moving closer to why we need the ratio test. So sometimes what may happen is that uh, suppose, so if you can find a r less than 1 such that ai is less than r to the power I, then it's very good, we are done. We can finish the question. You can
Hmm.
say it's convergent. And of course ai has to be positive.
Convergence.
ai is positive is needed because ai, if ai is 2 less, then it doesn't work. Okay, so it
Hmm.
has to be positive, then it works. So then we can say it's convergent, but sometimes we may not be able to find such an r immediately, in the sense that the first few terms they may not exist in r, but eventually that sequence may become tame. Okay, eventually it may be wild, but as you do some process, when it continues over on and on and on, it becomes tame, right? Or it just becomes more and more wild and it just goes to infinity, right? So this may not happen initially. What may happen is eventually this may happen, and happens in a lot of places. So I'll show you an example. Eventually this limit ai tends to infinity may be less than r to the power I, or some constant times. I mean, so what I mean in this case, what I want to say here is that that was not precise. I want to say something like this, that this may happen, that this limit is a constant, some finite constant. This is more likely to happen in the real situations. Like, eventually, it may not be able to, you may not be able to compare, but finally, this may happen.
Hmm.
Okay.
Okay.
Now, see, if this happens, then also we are good enough.
Hmm.
Why? Because if this happens, if the limit ai by r to the power I is equal to c, it means that um, let's say you take your epsilon to be 1. Okay, then it means that there is a n, right, such that for all n bigger than, there is a n naught such that for all n bigger than that n naught, ai by ri is essentially less than c plus 1 and greater than c minus 1. Okay, right? We can arrange for this for some n naught after some n naught. Now, of course, from here, it's very trivial that the series will converge, isn't it? Because c plus 1 r to the
Hmm.
power,
Okay.
so it's r to the power capital I. Okay. So you see why this is more powerful. Even if it happens in the limit, yeah, we are good enough. Okay. So what are examples where this happens? Let's take an example. So maybe I can remove the heading now because it's clear what we are doing. So for example, if you have a series like this, n by e to the power n summation n greater than n naught. Sorry, n starts from 0 in this, but it doesn't matter. This. Now you see, eventually I mean, initially we are not able to say that this is less than 1 by e to the power n, which it is not, right? It is not less than e to the power n. And we don't know what other series to compare it with. Okay, maybe, I mean, you can, maybe you can find something like e minus 1 by 100, and maybe you can prove that this happens. Okay.
Okay.
Yeah, and this seems correct, right? Maybe you can check it and it will happen maybe after n
Hmm.
equal to 5 or something. But this is again an ad hoc thing, right? Maybe in some other numbers you may not be able to. So so direct comparison with a geometric series may not be the most convenient thing to do. But if you take the ratio of this series with e to the power n, then clearly that ratio, no, what am I saying? So if you take the ratio of this series with um, no, not with e to the power n, of course, that will not work. Yeah, so if you take the ratio of this series with, let's say, I mean, you just take something slightly bigger than that, e by e minus 1 by 100 to the power n, then maybe it will work, right? So I mean, ratio meaning that the inverse of this, right? If you do this, then you see that this limit will be finite. Okay, this limit will be finite, but even here it is a little inconvenient because we have to guess this. Okay, we have
Yes.
to still guess this. It's the same thing as what I said earlier. So that my understanding there was a little, yeah. So so what we want to do is we want to make this check internal, meaning that we want to make the comparison internal. So till now we are making the comparison externally, right? We are comparing the sequence with another sequence. We are searching for that, and right, we are trying to find it. But at the end of the day, you realize that everything only depends on this r being less than 1. So can we make this check internal? So instead of checking AI with some RI, trying to figure out that RI, can we make it internal? That is a question. Because as of now, our statements are a bit like this. Logically, now if you think about this logically, Our statements are like this: there exists r less than 1 such that.
Sir,
Yeah,
I'll be back in a minute.
yeah, okay, okay, cool.
Just
Sure, yeah, sure. I'll also just figure my thoughts clearly. Okay, so Noel, is this, I think it's clear for you, right? If you have any questions, just ask us.
No, sir, no problems, but I'm just seeing it.
Haha, yeah. No, if you have any questions, yeah. This is easy
Yeah.
for you, I guess, till now, right? But still.
N upon, yeah.
Hmm?
Yeah. So
Yeah.
yeah.
Okay. Yeah. Oh, you
So
went to the park.
this is being recorded.
Yeah, I'm just recording it, just seeing how I'm, because this is the first time I'm teaching this ratio test thing. Okay.
Yeah.
Yeah. So I'm just is it okay if I'm recording it? Right? I think. Yeah.
Why should I have problems?
No, because you are also here. No, not problems, but I mean, if some student says don't record, then I have to think, right? I mean, of course, you will not have. I'm just joking, but yeah.
Yeah.
So you went to the park. I also
Yeah.
went out to just work out, but I came back.
I actually went to park to play football
That is very good, actually. Yeah, I should
from
play.
8 a.m.
Oh, you kept playing.
Yeah. I actually forgot about the class. Then I remembered.
That is good. I mean, it's good in some sense, yeah.
yes, sir.
Yeah. So, see, at this point, our checks are like this, right? There exists an R such that this is equal to C. This is better than the direct comparison. It is better than this, but still it has this universal quantifier outside. We want to get rid of this, and this is what we want to do in maths in general. We want to make our like our theorems quantifier free. I will give you an example. This may seem like, okay, why am I saying this, something like this, but I'll give you an example here. That's why it's called a test, because it's quantifier free. So just a very trivial example: when you have this quadratic equation ax square plus bx plus c, right, equal to 0, how do you write the statement that there is a real root? You say there exists an x belonging to R such that blah 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 is equal to 0. This quadratic is 0, right? Why is this not useful? It is not useful, we know, because this doesn't tell us whether it will have a real root or not, right? Means it's hard to check this formula, right? It depends on an external entity. So what we try to do in maths, as you know, we use the discriminant formula, right? We say that this statement is equivalent to b square minus 4ac is bigger than 0. Now this, you see, doesn't have any quantifiers, and that's why it is so good. So whenever in maths you're looking for a test, if you think about it logically, it's just like a quantifier elimination thing. If you can eliminate that somehow, okay, then your theory is simple in many senses. So yeah, this is just an outside point. So basically, thinking of that, what we are looking at is we can just compare the rates of the geometric thing and this, and thinking of that, since the ratio is less than 1, we guess this, that ai by ai minus 1 is less than 1, right? This is a good condition, right?
Hmm.
This is a
Okay.
good, it is internal condition, okay? This is a good guess, and in fact this works. We will prove it, okay? So what I'm saying is that if limit of this is less than 1, okay, so I should put the modulus, if my sequence has negative numbers or complex numbers, but for now we're just doing positive numbers. So this, if this limit is less than 1, then it implies that summation ai converges. Not a bad guess. We are just trying to mirror, instead of directly comparing it with the geometric series, we're just trying to pick up property of the geometric series, which is that the ratio is less than 1, and we're trying to mirror it here to make the matter internal. Okay, like instead of taking help from someone, you're just looking at them and copying it out this side. Okay, something like that. So this becomes a ratio test. Now, can you try to prove this, or at least intuitively explain or something how the proof of this will work? And then otherwise we'll just do the formal proof of this. Yeah. Or basically I can just replace this by AI is bounded. That's all, because we know that it's converges.
So our aim is here is to compare the given series with a convergent geometric series.
Yeah, that's what we started with, right? Yes.
Hmm.
But then we are trying to make that comparison internal so that we don't have to always go look outside for a geometric
Hmm.
series. Okay. So that's why this condition, this criteria is very obvious, right? This is what you should, this is the criteria that you're trying to mimic from geometry progression. And so this must be true. And it is true if we just look at a few properties of limits. So see, see, one thing is very, very important in this case is that this is a strict inequality. If this was not strict, this will not work, may not work. Okay, so the strictness is
Oh,
very
of
important here.
course.
So if the limit, so from here I'll just write a statement that I'll just write it straight away and I'll let you try to figure it out. There exists an n naught such that n bigger than n naught implies that an by an minus 1 is less than 1. Do you see this? Though this will not be very useful, but at first I want to see if this can be implied from the limit definition.
Yeah.
Right? Yeah. And even the strictness we can maintain, right? Okay.
Hmm.
But can we say something stronger? That is, can we find a R here? Can I say that there exists a R less than 1 such that, there exists an n naught blah, 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 such that this implies that this is less than R. Yeah, Noel, you can also think about it. Can we, if the limit is less than 1, then can we find a R such that we can maintain the ratio less than that R? Because we will need this R.
Shouldn't this be the absolute value of R or just
Yeah, yeah,
R?
but because all the terms are positive, this is the same
Hmm.
as, yeah.
Okay.
Um, yeah, but since all the terms are positive, we don't need that. Yeah, but yeah, in theory, yes, and that's actually very important. When we discuss absolute convergence, if we do, then that will be important there, right? But again, this is the important statement. And can you prove this? Why we can find an R such that this happens?
So,
Mm-hmm.
I mean,
Yeah.
this is correct, right? This is going to be because R can be R is less than 1 and an by an minus 1 is also less than 1. So it can be,
But no, no, no. But it doesn't imply from that. See, so if you just have an minus one less than one, then it doesn't
yeah,
imply that there will be an R which works, because there are infinitely many ans.
Hmm.
Right. So for see, no, I'm telling you. So it can be like this, right? It can be that an by an minus one is 1 by 1 minus 1. Then it is true that it is less than 1, or all an by n minus 1 is less than 1. But you can't
yeah,
find an R in this case. So
yeah,
this is
right, right.
so this is very essential here. That's why this statement is having a uniform bound is very important and very different. Okay. So, but we can arrange for that. Okay, I'll just tell you the answer because it's just a theorem we are proving, so it's fine. See, it's very simple because when this says less than 1, right? I mean, you can just say that it is equal to R or some R1 that is less than 1.
Yeah,
And you can use that. Now you can take an epsilon neighborhood,
Yeah.
right? You can take an R1 plus epsilon such that R1 plus epsilon is less than 1, and you can arrange for this. And this is your R, which is less than 1. So that small
hmm,
wiggle that we always
Hmm.
have in the real numbers, the denseness of the real numbers is important here. Not the completeness. Here, the completeness is not important, remember. It's about the denseness of the real numbers. That between any two real numbers, there's a real number. Okay. So yeah, now I think the proof is trivial, right? So we can just write the R here. Now I guess we can all complete the proof, right? Because now an is less than R times an minus 1, right? And an plus 1 will be R square less than an minus 1, right? Just an iteration, okay? An plus 2, I mean, so if I have to write the steps, then I'll just write, like if you're writing in the exam, you should write the steps like this maybe. Less than this, and then this is less than this. Um, No, 1, right? Plus 1. Yeah. And it is less than this. And you can just iterate. So these things are just algebraic. These are just the algebraic content of the matter, not very profound. Right. So from an, so from this an naught onwards, maybe I should write an naught onwards. This is less than a geometric progression times a constant. So it will be convergent. Okay. Any questions? Any questions? No questions? Okay.
No.
No, it's easy, right? So just the crux
Yeah.
is just, yeah, finding an R1. Yeah, so just when you go back and look at the notes sometime later, you'll realize that there's a very small crux that makes everything happen. And really behind the scenes is something, the quantified elimination, that thing is running behind. Okay. So here the quantified elimination was, but kind of, but you see, the problem is that I'll just bring this up. See, if this happens, then the series is convergent. The converse is not true.
So what did you say? Quantifier?
Elimination. Okay. Quantified elimination is what we are trying to do essentially, right? I mean,
Hmm.
on a very meta level, not important at all for here us, but it will be important if you keep the same philosophy, because if you see that throughout mass, this thing runs. See, this condition we are trying to remove, right?
Hmm.
We are
Okay.
trying to remove this condition. We are trying to form a statement which doesn't have the condition, this condition, and we have found an equivalent statement, and this statement is so much better. But then the same thing happens in when you're doing discriminants, or when you're attaching a dimension to something. There are a lot of places where you just remove the quantifier. And here our techniques to eliminate quantifiers is totally dependent on the interior of the subject. We are still inside the subject, right? When we are doing the quantifier elimination. But sometimes we can just look at the kind of statements that theory has. Number of statements, if the statements have a certain combinatorial structure, the sentences that you can write. So it means that basically a logician who doesn't know analysis can also prove the same thing. Okay, just looking at the structure where the sentences are made, and then he can show, okay, this theory will have a quantifier elimination. He doesn't know the proof, but he can I mean, he doesn't know the exact way, he doesn't know this exact statement, but he'll know that there will be a theory where you can write the same statement without quantifiers, and then he'll ask the analyst that, see, it's possible, now you try to find that exact statement. Very right. So this is how mathematicians collaborate, right? I mean, I'm not saying this is the only way, of course. I mean, I'm just saying, give an example. Okay. Yes. So I guess that's easy now, right? Okay. So what I was saying is that the converse is not true. Sometimes this test may fail. Okay. This ratio test may fail. Can you give me an example of where it fails? And if the statement is not clear of what I mean, then please ask me. So I'm saying that there will be series which converge, but this ratio is not less than 1. Okay. You can just think of very simple examples, and it will work. So I'll just write the statement I clearly here, AI less than 1. Okay, strictly less than 1 implies that AI converges. And maybe this time I can write it in the full capacity. The proof is the same, just the logical things you have to change. This and the other thing, yeah. Just think of any convergence series. Basically, think of any convergence series which doesn't look like a geometric progression, and that will be your answer. So this test is actually not very useful, and even the proof is so simple that it's not supposed to be very useful. Maybe then it diverges. If the ratio is bigger than 1, it diverges, right? You can prove it in the same way, exact same way. So you see, this test will mostly be useful in series which looks like this kind of series, isn't it? Like this kind of series, where when you take the limits, n plus n minus 1 e to the power n minus 1, then it's this, the ratio is not less than 1, but the limit is less than, the limit of the ratio is less than 1. Okay, so the limit is so this is just 1, so its effect is 0, and it's just 1 by e less than 1, so it works, right? So all those partial difference, the differentiations we do to sum these kind of series, integrations and all we do to sum these series, maybe if the techniques we learn, if you don't know, um, they are valid, is what we are showing. But if there is a series which doesn't look like a geometric progression and it converges, so an example of that would be, Noel, can you give an example of a series that converges, but it's not like a to the power something kind of series?
That converges. Okay.
Yeah, that converges, but it is not like a to the power n kind.
What if we define a sequence
Mhm,
an such
mhm.
that 1 by 2 raised to the power n plus 1 is if n is odd, and 1 by 2 raised to the power n if n is even.
But this will work in this case, right? This really works. This looks like a geometry. I know you're trying to make some changes here, but it still looks like a geometry progression. So the
What
ratio
about
test.
1
Mm,
minus 1 by n?
Sorry, 1
1
minus
minus 1 by
1
n.
minus 1 by n. No man, how will this converge? There's no chance. This is increasing. This is increasing sequence. So we cannot converge, right? It is getting closer and closer. No, no. Oh, so you're saying so? Okay, okay. What I mean is a series. Okay, maybe that was
Okay, okay, okay,
yeah. The
okay.
series will
Right.
obviously not converge, so I'm sure you can see
Yeah,
that.
yeah,
Yeah.
yeah.
No, no, no. So see, this example is also not good, right? Because I mean, obviously, just take the ratio and check, right?
Yeah.
All this
yes,
odd even
yeah.
thing will not work in the limits. So
Yeah.
you can just take a very simple. So in the beginning I mentioned slowly converging series or slowly diverging series. So if a series is slowly diverging, and then if you must tweak it a little bit and it converges, then it will also converge slowly. So what I mean is series like this, and I'm not doing the proof right now. I had given this as an
Oh,
assignment.
okay, okay, okay. Yeah, yeah, yeah. Yeah.
Yeah. This will not work. There's no chance to work with geometry because this converges very slowly. Okay, but the
Yeah.
geometry progression converges rather fast, right?
Mm.
And you can just check it, right? Because if you check 1 by n square and n minus 1 square, by sorry, n minus 1 square will be the
Pi
numerator.
square by 6. It's
No, that is a much harder thing. Okay,
yeah.
and 5 square by 6.
So
Huh?
so we can just take 1 upon sigma 1 upon I to the power delta, where delta is less than 1.
Bigger than
Less
one.
than or
Bigger than
yeah, bigger
bigger
than
than one. Yeah. And I think I had asked you to show that this is convergent, right?
yeah, yeah,
In the problems I had given you this one. I had given 1.5 here, but in the proof you will see that it really doesn't matter. Yeah.
Mm,
yeah.
So
problems given to me?
yeah, yeah, yeah. Oh, you didn't see
Oh,
that?
I
Last
haven't.
set. Oh no, I gave some
No.
set of interesting questions. Oh, that's why maybe all of this is not. Yes, I had like properly planned that so that I've not discussed the problem set, but I'll just show you the
Mm.
problems I gave you. Oh, so you didn't see that yet.
How is this pi squared by
Okay,
6?
that is a little difficult to show. Okay, so I
Yeah.
mean, technically, why you can think that pi square will come in the picture, because if you plot these things, they kind of form areas of a curved figure. Okay.
Yeah, Euler proved it with geometry, right? So it's going to
Yeah, yes, his
be
proof was, I mean, wrong, but geometrically means it is not very unobvious that it should be not be pi square by 6 is what I'm trying
yeah,
to say. Okay, like why the number pi pops up. So if you just plot these one by, the graph and so on, right? Okay, sorry, what am I doing? It will be 1 by x square graph, right? Like this,
yeah, 1 minute,
right?
yeah, like that.
So it will be like this, right? The graph, it will, so these areas you're adding up. Right. So it turns out it's biased. The
Mhm.
exact proof is not, I can give you a lot of false proofs, but the exact proof, there are some tricky proofs. Maybe I'll give you in the homework to try how to prove by using some steps. Okay.
No, I showed you by complex numbers, right? One
Yeah,
good
yeah. That's
proof.
what I'm saying. That's a tricky proof. Yeah, yeah, yeah. So
Yeah,
that proof I can let her try. That kind of proofs they can
yeah,
ask in the exams with some hints. Okay.
yeah, yeah,
Some identities, trigonometric. But that's not, but that's that kind of proof is not very useful to understand mathematically. Understand mathematically, you could
yeah,
use complex analysis and all that. So, but
yeah,
anyways, we can yeah, that is, but to show, but see, that is the whole point of our discussion, that we don't want to find the series, we want to show it is
yeah,
convergent, and
yeah,
showing you that
yeah,
is convergent is very much easier. Okay, so that is really the crux of analysis, right? That you can show things without actually, finding what the exact limit is. You can show that the limit exists. So,
Yeah.
oh yeah, so the mistake I think I had made, I had numbered that as a problem number 11, set number 11. And I had
Mm.
given her the problem set 12 and I round numbered it wrongly somewhere. Oh, maybe I did not send it. Okay, okay. Oh man, what am I doing? Wait. It is here, it is here. I did not number the problem set. No, wait. Shoot. Okay, anyways, I can't find it right now, but I had made it. Probably I forgot to send you. Okay. So I'll just send it later. Okay, just after the class I send it. Okay. So yes. Right. So that's what we're discussing, right? That the ratio test is not a sufficient test. Okay. So yeah. So let me just clear the page and let's move on then. So I did not send her the paper. There were some interesting questions I had made. Anyways. Okay, so never mind. The what I'm trying to say here is another thing that so basically here you understand that where you should try the root ratio test and where you should not try, that kind of thing
Yeah.
also we are
Yeah.
understanding, which is
Mm.
probably the most crucial part for us. But all that apart, there is this thing that, see, there is this limit less than one, it implies that it converges, and if it's bigger than one, it implies that it diverges. So this gives a sufficient
Equal to.
condition for convergence, right? If
Yeah.
this something happens, then it converges. But as you
Mm.
saw, that there was some series for which it did not work,
Yeah.
right? So in general, there is a theorem that says that any test, now for that you have to define what a test is. Any convergence uh, test will not catch all convergence series. So there is no test which actually can work in all convergence series.
Is this a theorem?
Yeah. So
But
this is not like
this yeah, this doesn't seem to be easy to prove. I
no,
mean,
this is not easy to prove. Okay.
yeah.
There are some tricky proofs again for every. There are some tricky proofs, but the real proof is also not easy. Tricky proof is also not easy. But can anyone try
Yeah.
to expand on this? Because again, this statement itself is not very. I've not written very formally intentionally.
Expand, like, what do
Like
you
what does it,
mean
okay,
by
so I mean, can you okay, let me try it. So what I'm saying is that if you take the collection of all convergence series, let S be,
Mhm.
S is a convergence series. Okay, convergent series. Okay, and let T be so T is a test, right? And let ST be the collection of series which S satisfies this test. Okay, satisfies the test T, the set of
Hmm.
those series which satisfy the test T. So obviously these series will be convergent, but I'm saying that this will always be a strict subset.
Hmm.
Hmm.
Right.
Okay,
Yeah.
okay, okay. You can find better and better tests. You can write longer and longer proofs, but it will never be enough to catch all the series. Now, this again has a deep logical meaning. Okay, but yeah. So that's but okay. This is the thing.
This is
See,
more like logic
this is more
and
like,
less of logic.
it is less of analysis and more like logic, yeah, but even, I mean,
Yeah.
analysis can be used in the proof. Okay, but logical proofs also are there because the collection of all convergence series has a certain size, has a certain cardinality. Okay, that can be
Oh,
shown as a
okay.
certain cardinality. And
Yeah.
every test you write, you can show that every test, if you define a test logically, then it's basically like a finite letters you need to use, right? So now using
Hmm.
combinatorics, infinite combinatorics, you can count how many possible tests will be there. And now every test will only capture some countable or certain size, certain cardinality number of series. So you can multiply those size to so that the set of all tests that can be captured, series that can be captured by all the tests is certain, has a certain size. Or rather,
What's infinite combinatorics?
so infinite combinatorics is just cardinality of infinite sets, because like just proving that the cardinality of r cross r is same as r.
Hmm.
Basically this, we are trying to construct bijections, and if you do this math, you will
Hmm.
see that it requires some clever construction of bijections. Of course, there we use some axiom of choice and infinite versions of mathematical induction and so on. But I'm saying that using that kind of argument, bijection, injection kind of arguments, you can show that based on size itself, this is not possible. Okay, so that's the proof
We
logic.
proved that n into n has the same cardinality as n
Yeah, yeah,
Okay.
by establishing a
yeah. But
bijection
again,
and
if
all
you if
that.
you, if you think that the proof was also a bit combinatorial, right? I mean, you gave a number
Hmm.
theoretic proof, but that's also like a discrete kind of argument you did. So in general, we have to do those
Hmm.
kind of arguments. So this is like infinite combinatories. At least one part. There are many other things in that which I have no idea about. Okay.
Ah.
So this, but you see, personal analysis will prove it like this, that something like this, that, and this even you can think about. This is a good question on its own. So it's like this. Basically, I'm saying that given a series, let's say there is a series a, there's a an and summation an converges. Okay, okay, and satisfies test t. Okay, then you can find the series bn. Okay, you, and this can be actually shown, and this follows a bit from one of the exercises I gave you, Cauchy condensation test. I'll send you that again and you'll see. You can find a series bn, okay, such that summation bn also converges, okay, is convergent. Everything is positive here for the time being, just to make things simple. Also converges, but bn, the decay rate of bn, or bn converge, or bn converges much slowly. What I mean is an by bn would be infinite. Just limit of an by, not the summation. Obviously not the summation. You see.
Could you elaborate on
Yeah,
this
yeah, yeah.
once
So for
again?
example, let's say that an converges. So if an, we can take r to the power n, r less than 1, right?
Hmm.
You have this. So an is converging. Very good. Now I will say that there is another convergence series in the class which also converges, but it converges much slowly than an. Example, 1 by n square. If you take the ratio, it goes to infinity. I
Hmm.
mean, yes, obviously, right? You take the ratio and see, right? It goes to infinity. R to the power n. Wait, no, 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 no. 1 second. It does it go to? So I'm just saying that there will. I'll try to come up with an example, but let's explain the statement. R to the power n. Okay, this is convergent. This is converging summation R to the power n converging. I'm saying that you can find another series which also converges. Bn also converges, but it converges much slowly, right? So I think I have written the wrong statement here. 1 second. So an converges and bn converges much slowly. Okay, so I'm very sorry. This should be 0, right? When bn converges slowly, I mean that an will be bigger. Oh wait, uh,
It
wait.
should be infinity for
It should be
an to.
infinity. Yeah, yeah, yeah. 1 second. So if an is converging
And Bn
okay,
converges much slowly.
much slowly, which means that no, no. If bn converges much slowly, it means that bn will be bigger always. Okay. Yeah, yeah, yeah.
Uh,
Do you see this,
yeah.
right? So bn converges slowly means that bn takes more time. Uh, bn converges slowly. Yeah. It. I'm trying to say that bn is bigger than an, kind of. Okay. Bn is bigger than an, but still summation bn also converges. Okay. Is that
Okay.
does that make sense? And you
Hmm.
see what I'm trying to say? So an is a series that converges, and an is caught by the test t. Bn also converges, but bn is bigger. So it means that the convergence of bn will not follow from the convergence of an. You see this, right? The convergence of a, because bn is bigger than an being less than infinity will not imply that bn also converges.
Hmm.
Okay, though I have stated that bn converges, but it will not follow from the convergence of an. Okay, now if bn converges so slowly, which means that bn is remains bigger, so it takes more time, right? Remains bigger. If bn remains bigger, um, if bn remains bigger, then bn by an should be infinity. Yes. Okay. Yeah. So now after explaining, it's quite clear that it should be like this. Yes, this should be infinity. Is it clear, right? So if we want a sequence which is not caught by the test, then we take a series which is harder to prove convergence, right? The convergence of Bn would be harder to prove, isn't it? Okay. So if Bn is bigger than An, but moreover, if Bn is much bigger than An, which means that the limit becomes infinite, then the test T will not be able to capture the convergence of Bn,
Hmm.
right?
Okay.
Because this test T will have like some ratio less than one. So An will satisfy that ratio, some
Huh.
test, but Bn can never satisfy because infinity will just destroy the entire game.
Mm.
Okay, so the convergence of Bn must be will be harder. So maybe converges slowly is not a good word. All I'm trying to say is that Bn is harder to show that it's convergent. Okay, so that is what I'm trying to show. Yes. Now let me just see if this example works. So finding examples of this are not easy. That's why logical proof is better in this. But analysis proof is also there. Let me just try. So if this is our sequence an, right? And certainly 1 by n square is bigger, right? 1 by n square takes more, like it has big values, right? So if I do this, I am not sure if this happens, but you see 1 by n square is the bn, divide by the an, r to the power n. Now clearly this is 0, right? This goes to 0, right? The denominator
Yeah,
goes to 0, and so the numerator
Mm.
goes to infinity. There's your
Mm.
example. These are the
Mm.
kind of questions this can be asked in exams. These are like an exam. This doesn't need any analysis or any ratio test and so on, right? But the meaning of this is this, okay, that this will not be caught by the ratio test. And in this way, I'm saying that it's for every test. Now, how you prove that, that's a little difficult. I mean, at least we need to do more problems before we learn. I can give you a construction maybe, but then it will are not motivated. Okay. So, but this is a really profound thing. And this will really prove that, right? That no test will capture everything. Of course, we have not yet defined what a test means very specifically, but that is, yeah. Okay.
yeah,
So this is really what the interesting thing of the ratio test is all about. Okay. So, um, I think I should stop the ratio test now and go to the root test. The root test will not take more time because root test, now we know how tests are going, right? Soon, now after some time you
You
can,
said that we
yeah.
haven't defined what a test is. What does that mean?
Yeah, so how would you define a convergence test? We have given examples of convergence tests, right?
Hmm.
But how do you define a convergence test? How do you make a definition of all those conditions that are given? How do you capture it with some finite number of statements? That's not clear. So you have to probably say, like, there is a parameter rho n such that if an, such that if there is a formula which can be written with finitely many statements in real numbers, and some finitely many quantities, such that if that parameter satisfies some bound, it implies that summation an is something like that. You have to say, because you're really trying to define something which has so many possibilities, right? It could be so many kinds, like the root test says some this kind of formula. Ratio test has this by this kind of formula. Some Rabbis test or D'Albert test or some other kinds of formula. You have to really go into the logic of it then, right? If you want to formally, but that will not be, yeah, good for us maybe. Even I'm not very comfortable with that probably. Yeah. Yeah. Okay. Okay. It's fine. But you see that where we are lacking a little bit, but we are trying to get the stuff done, moving things forward still. Okay. So that was the view of the ratio test with the motivation, problem solving aspect, and the logical side of it also. Now the ratio test. Now the root test is a very similar thing, and of course there are many variations of this. Okay, what do you do when the limit doesn't exist and all? I'll give that in the problems, like lim sup you have to do if the limit doesn't exist and things like that. So that we can do in the problem sets, because yeah, just want to make sure that we are understanding the thing and enough to do the rest of the things ourselves. Okay, that's so. Now the root test is, just very simple. Yeah, so basically the root test also is comparison with the geometric series. Okay, but as the word root suggests, it is you have to take the roots. Okay, so I'm not giving too much motivation here because I think, once you see it, you can feel it. Hmm. One second. Yeah. So instead of taking the ratios, we are taking the nth root. So if you look at the property of this r to the power n, right? Where r less than 1, this series, right? So the other way you can mimic it is this is less than 1. Right. Other way in which you can mimic the comparison, make it internal, is this is less than 1. Right.
Hmm.
So that's what we are trying to do here. Okay. And this is really, yeah, we are trying to abstract a property from here which will make it work for other sequences. It's just like an abstraction process. Okay.
Hmm.
So if this limit, okay, so not equal to 1, I'm sorry, this root test is more
Yes.
powerful. Okay, is more powerful than ratio test. More powerful. Okay. I will give you in the problem sets to try to show some with some examples why it's more powerful. That's an interesting thing. But yeah, so if this is, but again, this is will not work for all. Okay, you can always find examples, and yeah, that we will see in the problems again. I'd already given you that, but I forgot to send. So this limit is less than 1. It implies that summation an converges. Okay, so in this since we have grown a bit of intuition in this thing, so probably I can at this point, and I can put a mod here. Okay, and so then mod an converges. Okay, now now if all the, now in this case I'm not putting the condition that all ai's are bigger than 0. I'm just trying to make us go outside that assumption, because a lot of good analysis is really done when you're in the complex plane. Okay, really, right? If you think about it, -1 times -1 is 1. You can prove it, right? But really, the feeling of it really comes when you see -1 multiplication by -1 as a rotation by 180 degrees, right? And then you rotate again when you multiply by -1. And to be able to imagine this, you have to go in the complex plane, right? It becomes more clear when you put the line in the complex plane. So like this is a very stupid example, but like this, there are many other things in the reals which can be understood better if you go in the complex plane. But of course, for that you have to do some complex analysis. At least there are, yeah, on a trick level, as you can see, it's used in Euclidean geometry and so many other places also. But anyways, that aside, I'm just trying to show that now what I'm trying to show here is that summation mod n, if you forget about the test for the time being, summation mod n converges is not the same as summation an converges. These two are different things. Can you show me how they are different? Like basically give an example where one of them is true but the other is not true. So these two are independent. Okay, let me just use all those words, just that these are different. Is different, okay, from this. So just can you come up with an example? Then I can just state and prove the root test. That's not very difficult. Noel, do you know any examples where mod and
Yeah, I'm just thinking. I mean,
yeah, yeah,
I
yeah,
don't remember
yeah.
any.
Yeah, Maima, you may have not seen many examples, right? Where, so really, I
Hmm.
mean, for this one, you will really need an example where the series is not all the terms are positive.
Haha, that's
Yeah.
what I'm looking for.
Yeah, yeah. So yeah, if you have not seen, then might be a little difficult for you. But let's see.
So we can just take that sequence.
Mm-hmm.
1 minus 1,
Mm-hmm.
1
Plus
minus
half,
1
-1/3.
plus half minus half. So this will
What? Plus half,
uh,
minus half? That what?
plus half minus half. Yeah, yeah. Plus half minus
Oh,
half.
what kind of series is this?
Yeah. So
How?
what will
Ah,
happen is
okay.
the
I never thought about this example, but this seems interesting. Okay.
yeah. So this will this by taking the mod and adding, all of them will diverge, but individually it will converge, right? I mean,
Okay, let's prove this. So, okay, you have given two statements. So, number one statement I think is clear, right? Mod So if this is a1, yeah, this looks like a, you might say this is 0, but we have to think more carefully.
Yeah, yeah.
Mm-hmm.
Okay.
Actually, we can't add infinite things, so
Yeah. So we have
that
to you have to take the sequences, and there are one monotonically increasing, one decreasing.
yeah,
So anyway, but yeah, I've not discussed alternating series conversions, but just it's okay. We don't have to discuss everything very formally. This is the thing.
yeah.
Clearly, mod AI summation, mod AI diverges, so that we can get out of the way.
Divergence.
Okay,
Yeah.
so that's fine. Okay, now how do you prove that this actually converges?
Hmm.
So this converges, we want to prove. So we can just use the
Yeah, yeah.
definitions. Yeah. So here we will have to use the definitions, okay? Because our mod linear is not converging. So our tests till now what we have done will not work. Okay. So we have to use the definitions.
How do we know this converges?
No,
We don't know
we
yet.
want to prove it.
We have to.
Yeah, we don't
Yeah.
know. So I'm saying that just try to take the partial sums and see, right? So if you take the partial
Partial
sum
meaning
one,
positive and negative.
no, not
Oh,
positive and
oh.
negative. No, so
Okay,
let's
okay.
take the
Partial. Yeah,
so
yeah,
I'm
yeah,
saying
yeah,
that let's say I also don't know at all. Okay,
yeah,
let's just take the partial sums and see, right? Because
yeah,
we don't want to take any risks in this. This is an alternating series, so we don't want
yeah,
to use too much intuition in the beginning. Yeah, let's
yeah.
take the partial sums and see what is coming. Um, S2 is 0,
Half
S3 is half, S4 is
zero,
0, right? S5 is 1
1/3.
by 3, okay, and so on. Now tell
Yeah.
me, is this partial sum series sequence convergent or not?
Actually, yeah, it's convergent
Obviously, it is
because for
convergent,
2 yeah.
right? It is
Mm,
S2
going
and
to 0.
2. Yeah.
So see,
Yeah.
I think it is convergent. Okay.
Yeah.
So this
mm,
is so sometimes they can ask this kind of, but yeah, one of course, one minus one, one minus one, one minus this will not be convergent.
Yeah, this
Okay,
is
of
because
not.
you take the
course.
partial sums, yeah. So this is very easy, but just that we shouldn't. Let's see here, the knowing the exact definition is very useful. Otherwise,
Yeah.
or what is the definition you're thinking about? And then we'll ask our question, ask ourselves, do we even know what convergence means? Yeah.
Yeah.
Okay. So this is
What?
no, I mean, I'm saying that if we did not know the definition of convergence, and we sometimes we study the whole chapter without
Okay.
doing, then in the exam you think, what does convergence mean? This question, this kind of questions can
Mm,
make us ask those questions. And actually, those kind of examples are given in the books before they define convergence, just to motivate the definitions, unless it's a Rudin kind of book. So, anyways, this is the thing. So these two are not different. These are different statements. Okay. However, the the first one, now this is an interesting one. The first one implies the second, as one would guess, but how do
Yeah, actually, yes, because in
because
mod n,
it's more,
the negative terms would obviously, I mean, decrease the
decrease
chances
the
of
chances.
being
Okay,
correct.
yeah, so this is intuitively clear. How do you prove
Yeah,
it? So think about this for homework. Okay, why this is
yeah,
and apart from a proof, you can also try to and this will really need a new technique as far as the proof that I know, but let's see. Okay, so think about this. Okay,
yeah,
that why this is true. This is really very deep in some sense. When you see the proof, when you do the proof, let's see which proof you do, then you can see. So I've just saved the screen and done it, and I'm removing it, so it will be there in the when you see the
yeah,
note. Yeah. So I think now we can stop this and just go to the. So I'm just saying that all these tests are for absolute convergence. With the mod, it's called absolute convergence. So there's absolute convergence, conditional convergence. Then there is uniform convergence when we have convergence of functions. So there is a lot of interesting things there. And then there's a pigeonhole missile kind of statement called the Baire category theorem. There we see that small point-wise convergence will imply that there is a uniform convergence in a small place in some interval. So we will see all that maybe later. Very interesting results. So this is what it is, convergence. Let's see the proof of this. Very simple proof, not deep at all. So basically, again, right, probably you can just write the proof yourself at this point. So this is less than r, right? For some we can just sum n bigger than n naught,
yeah.
and then it's done, right? Just take the mod, open the mod, send it here,
Mm,
add it up, finish. The proof is simple.
mm,
Even the motivation is quite simple. Okay, but these
yeah,
little nitty-gritty details are important, and these are actually what are asked in the exams, at least in the B math, and they won't ask the root test directly, even though you can use it cheaply in this quick to get a quick proof of something. So yeah, that's what I wanted to say for today. So the root test is over, the ratio test is over, and we discuss some other things. Um, yes. So yeah, quickly, I think we can just do one more. Okay, just we can just do one more test, and then we can, because we want to just move on a little faster than what we are doing. So, but anyways, let's see. So here, since we have gone into conditional convergence already, let's say that your sequence. Let's say if you have a sequence like this. Okay, 1 by 5 minus 1 by 6. So I'll just come in 1 minute, but meanwhile, just try to think of a proof of why this is convergent. There are many proofs. Okay, just try to think. Okay, I'll just come in 1 minute from the washroom. Okay. Yes. So again, any proofs? Hmm.
So probably we can write this as sigma 1 upon 2n plus 2n minus 1,
2n
1
minus
upon 2n 1 minus 1 upon 2n.
No, you cannot write.
No, in a single sigma,
Oh yeah,
not
yeah.
in a.
Again, no. This also you cannot write because here you are going to use the associativity, right? You're going to group it like this, right? You're going to group it like this. So you are saying that first you will add these groups and then you will sum.
Yeah,
I will don't think that we are allowed to do that because when you do that, let's think of what this implies algebraically. Maima, are you there? Yeah, yeah, I think you are there. Yes. Okay. So,
Maybe what
mhm.
we can do is we can add all the terms like 1 plus 1 by 2 plus 1 by 3 till 1 by 2n.
No, but that doesn't converge. Okay. But yeah, go on, go on.
And then maybe you can subtract.
That is
uh,
exactly what you cannot do. No, that's not allowed because there you are using the commutativity of addition, right?
uh-huh.
That's not allowed at all because see, this is the whole thing. See, even that's far fetched. Even this is even what Noel is doing is slightly is not allowed because see, what he's saying, He's saying something is like something which is much tamer than that, right? He's saying I can group the terms like this and add them, okay,
Hmm.
and then I'll add the series. But the problem with this is when you are doing this, you are only looking at this partial sums. Think about it.
Hmm.
Right? You're only looking at this partial sums. And if what you are doing, then that's even completely more different. You're not even looking at the partial sums then. Right.
Hmm.
So yeah, that is those things are
So,
not. Hmm?
one other thing we can do is we
Mm-hmm.
can say 1 upon 2n minus 1 minus 1 upon 2n,
One upon
without taking the summation. Without taking the
uh-huh.
summation,
Without taking the summation.
any
Yeah.
I'm just taking a general term.
Okay. Yeah.
It's less than 1 upon 2n square.
But again, you're doing the same thing, right? It's the same
Actually,
thing. You're bounding on this,
yeah,
right? And
yeah,
then you'll add
actually.
it, but then you're only considering the even subsequence of the partial sums.
But isn't that so? It is basically comparing it to a geometric sequence, right?
No, no, you're comparing, but you're only taking the even terms then.
Yeah,
Right, that is the problem. Then you have to check for that. Yeah, that will work. Then you have to check the odd things also, odd partial sums
yeah,
also. And if we show that
yeah.
both of them converges to the same place, then it will be accepted. See, we were doing all these things, we were doing all this grouping and all earlier. There it did not matter. That's why we did not really pay close attention. But here it matters. Okay. But yeah, I mean, but the ideas are all makes sense. But so
Yeah,
one proof that is like a very simple proof is that this is equal to log 2 minus log 2
yeah,
square.
that is
But it's
there,
not a
but
good proof by any
not
means,
really
because before that you have to show that something converges, some power
it's like
series.
saying 1 upon 1 square plus 1 upon 2 square is 5 square
Pi
by
square by
6.
6, yeah, it is something like that, but this is obviously not a good proof at all. But in a very in dire situations this might be save us. But yeah, so how do we give a proof of this? Even I don't know, I have to think. So there are many proofs that can be given. Let's see. So uh, hmm what proof can you give for this? Hmm. So the root test, ratio test, all that will not work, certainly. Uh, yeah, I mean, I have a proof that follows from a result, but we don't want to do like that. We want to get to the result from this problem. So, hmm, yeah, let's see. So, hmm, 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 okay, let's see. So let us look at the even subsequence. Let's look at the odd subsequences, or let's look at the even subsequence only, which Noel was saying. Okay, let's say we have S2, S4, uh, S6, and so on, right? So if you look at the even subsequences, then can you say something about them? Can you say that whether they're increasing or decreasing or anything like that?
They'll certainly be decreasing.
Decreasing.
Uh, Increasing.
In Yeah, increasing,
Oh,
sorry.
oh yeah, it's
Yeah, right.
increasing.
It's increasing. So S2, S4, S6, and so on. This is increasing. And can we also show that it is bounded? They are all bounded by something. Can we show that?
Then we are done, right?
Then we will be done with the even one. Yeah. Then we have to check the odd one and show that they have the same limit. Yeah. So yeah. So
Yeah,
can you show
that's there.
boundedness? So I'm just following from the idea of the even subsequence which Noel started with. Okay. So even subsequence, I'm saying they're increasing. Can we show they are bounded? Just use some logic to maybe say that. Can we say that this is bounded till 1 by 6? Hmm. Any bound will work. Right? Can you say it is less than 1? right? It's always less than 1, isn't it? Because from 1 you're subtracting half, but you're only giving 1 by 3 back, right?
Mm-hmm.
And then you're subtracting 1 by 4, so you have to give 1 by 4 but only giving 1 by 5 back. So
5.
every point will less than 1. This is like a logical part. Okay, I mean logical meaning combinatorial or whatever. This doesn't one. So this is convergent. Yeah, it's clear, right? This is convergent. The even subsequence is convergent, but we don't know the limit. Okay, and the limit is that log 2, that thing. Okay. um, Now you can do the similar thing for odd subsequence, right? What can you say about the odd subsequence? With alternating series, this is usually the trend. Okay, but yeah, we will derive a theorem and we will see. Can we say about this one?
Yeah,
So what can we say about this?
it's going towards 0.
It's going towards no, it's decreasing. You can say
Degree.
right. It's decreasing is clear, right? I'm not only if it's going
Hmm.
towards 0. It's certainly decreasing, right? Because you take 1, and the next time when you're taking, you're adding a negative number, right? And the next time you're adding another negative number, right? So it's decreasing, right? So S1 is bigger than S2 is bigger than S3, and you can just show that it has a lower bound somehow. Okay, I'll leave that to you.
Hmm.
Show that it is greater than 0 or something by some similar kind of argument. So yeah, so the odd subsequence and the even subsequences both have limits. What limits they are, we don't know. So we don't know that. Now what we want to show is that they have the same limit. We don't care about what the exact limit is because that will be then finding the answer of the sequence, right? We just want to show they have the same limit. Okay. So yeah, so how can we do that? That they have the same limit. So two sequences whose limits you don't know, but you want to check they have the same limits. So again, I mean, people can come up with it, but I'm just writing it out. You just subtract the corresponding terms, right? So if there's a1, a2 dot dot dot, and there is b1, b2 dot dot dot, and if you want to show they have the same limits, usually the best way is to just subtract and show that the limit is 0. Sometimes the ratio is a better way. It depends on how the what arithmetic is dominant there in that problem, right? Here the it seems like addition subtraction is good, right? It's all like that. So we subtract the sequences. So we subtract the corresponding terms. The corresponding terms will probably be 2i minus 2i minus 1. I may be off by 1 plus 1 minus 1, but yeah. So this we want to show that this is going to 0, right? Limit is 0. Then we'll be done, isn't it? Okay. Is it clear for everyone? Noel, you also, I think.
Hmm.
Yeah. Okay. I think he's on mute. Maybe he doesn't know. But anyways, it's fine. Doesn't matter. He's I think
Yes, sir,
busy.
it's fine. Yeah.
Yeah. Okay. Yeah, it's clear, but I'm just still just asking because yeah, fine points here. So yeah, so we want to show that this is equal to 0. So general problem solving trend also. Now this is very simple, right? Because when you subtract these two, what is left? Just the just the ith term is left, right? This is I mean the difference is just a 1 by 2i or
Hmm.
minus 1 by whatever 2i. This is obviously going to 0, right? So
Yeah.
yeah, right. This is the good thing, we don't know what the limit is, but still we, came out victorious. So yeah, but really, let's abstract the principle from here. The principle to be abstracted is that why was this increasing? That is a key. Why was this increasing? So you see, this was increasing because the sequence was alternating and decreasing, right? So because the terms were alternating and the terms are decreasing, right? Which means that a1 is bigger than a2 is bigger than a3 is bigger than a4, right? And the sequence is like this, right? a1 minus a2 plus a3 minus a4 and so on, isn't it? That's why since the sequence is decreasing, that's why if you take the events like this first block, second block, this will increase, right? Because this is decreasing, so this is positive.
Hmm. Okay.
That was abstraction. So if the sequence is, if the terms of the sequence, I mean, if without the sign, unsigned terms are like this decreasing and the terms are alternating, then these two things will happen in both the sequences,
Hmm.
right? They will be like this and they will also be bounded. The boundedness really just comes from another thing, which is again a very obvious property to put in a sequence. That is limit ai is tending to zero. So if this property is not satisfied, then you don't even need to do anything in the problem, right? If limit ai is not zero, then the series can by no means converge.
Converge. Yeah.
There is this, then we just don't even need to look at the look any further. We can just say from there. So that is obviously has to be there. And this was the second abstraction. And really, this property was really what allowed us to conclude this, right? That both the odd and the even sequences have the same limits. That was the basically the property that the terms are going to zero. So in fact, any sequence in which any alternating sequence like this in which it's just decreasing and the terms are going to zero, it implies that this will converge. Well, I mean, this will converge, meaning that the partial sums will converge, and this is the symbol for that. Will converge. Okay, so I hope this is clear. Right? This is called the
Hmm.
Leibniz alternating test, something like that, alternating series test. Okay, but we really are seeing that it's like an abstraction from something, and now we don't even need to do a proof of this. You can do it when you want. Okay, you can also try to see it pictorially, try to draw a graph. Maybe I'll give it through indirectly through an example, and there you have to, this will be, you can model that here and you can realize that it can be modeled like this, can be modeled back to that. Okay, so yeah, this was the thing about series. Mostly we are done with series. Yeah, there is one two things are there, rearrangements and so on, which I will do in the next day, means in infinite series only. And then by that time we will move on to other things like limits of functions and properly. Okay, yeah, and I'll give you some problems. And
Okay.
also about the application of recurrences in series, which I had discussed one problem of, but I did not give you any other problem. There are many problems like that floating around, like in the, if you look at tomato and all problems are there, but I'll just give a few of my own just to make sure that what I am teaching, that concept is used there. Okay. So yeah. Okay, then see you next
Okay.
time. You can tell me when you want the next class, and we can cooperate that with Noel also, and we can continue the thing.
Hmm.
Okay.
Sir, in this 1 minus 2 plus 1 by 3 minus 1 by 4, I was trying to find a sequence in X that when integrated forms this and proves that the original sequence is convergent.
Yeah, that is a good way. But the problem is that when you're integrating, you have to prove that you can split the integration over all the terms. Right.
Uh, that we assume, right? We
No,
mostly
that
assume.
is a much bigger assumption than then you can just assume that this is convergent.
Yeah, yeah,
I mean,
exactly.
that is like a
If
very,
we,
yeah. So like what he's saying, which is actually a good way to find the answers to these kind of questions. But yeah, is that when this series is there, he's saying you can integrate this and split it over all the terms. So that's a result that we'll prove sometime later. Okay.
yeah,
That
we can't split summations and we are talking about
yeah.
integral.
Basically, it's a matter of two operators commuting, summation
Yeah,
and the, yeah, it's basically a matter of that only. So basically,
yeah,
commutation of operators is always a desirable thing, be it in algebra, vector spaces, or wherever you are. But we'll prove that it happens in that case under some conditions. With derivatives is much more difficult for certain reasons. We will discuss all that when we get there. Yeah. Okay.
yeah.
So see you next time then. I hope you like the class.
Okay, sir.
Okay. Bye.
Yeah,
Okay,
okay.
so
Bye.
thank you.
Yes. Bye.
Thank you.